So our last talk is Jordan. Something about electronic traffic jams.
Yes.
Sounds interesting.
Hi everyone. This work is grouped under these new strategic research themes. This is grouped under what's known as the emergent quantum phenomena stream. And so I'd like to say a few words first to begin about what emergence really means. So as we know, there are four fundamental forces in nature. But despite the strong and weak nuclear interactions creating and governing the nuclei of atoms around us, and I wouldn't be standing here without gravity, literally. It's the electromagnetic interaction that governs almost everything in our lives, all the matter around us that we can see and touch. In particular, if you allow for a little bit of quantum mechanics and some relativistic corrections, everything pretty much boils down to the Coulomb interaction, just everything that we remember from high school. Now, this interaction, being fairly simple, it doesn't just work with two particles. In fact, it extends as you add more and more and more into the system, as we build up matter. Even though the complexity increases, the fundamental rules have not changed. We go from this to all of condensed matter physics and chemistry. But there's no reason to stop there. There's no new laws as we move on to biology, nor even to neuroscience. And yet, you'd be insane to insist that you could go from the Coulomb interaction to understanding the human mind. Now, this gives us a good example of what's known as emergence. At each level of complexity, despite there not being any new fundamental interactions, we have new fundamental concepts and a new context that is just as fundamental as the layers that came before. And this was perhaps best elucidated by Philip Anderson, while a visiting professor in this department back in the 70s, when he wrote his seminal paper called More is Different in Science, where he laid this out. The same extends in emergent quantum phenomena, where we deal with mostly either with cold atoms or with electrons in materials, where we start with a high-energy microscopic picture of the Coulomb interaction, and yet at low temperature and low energies, we get into all sorts of ground states with entirely different symmetries and structure from what you would expect just from looking at the interaction itself. These sort of emergent ground states, such as superconductivity and magnetism, many of which are highly quantum mechanical in nature, there's no way that one would expect it from here. And so this is an example of the work that we do in the quantum matter group, is characterizing these sorts of states and tuning between them. And here we see some recent work from this group, such as work on quantum trichedral points in ferromagnets from Malte Grosch's group, Fermi surface signatures in correlated insulators, which shouldn't have Fermi surfaces, from Suchitra Sebastian's group, ferroelectric quantum criticality from Montu Saxona's group, emergent charge order in quantum magnets from Sean Dutton's group, structural quantum critical points in superconductors from Mike Sutherland's group. What all these things have in common is that we're examining these different emergent states of matter and tuning between them using either pressure or electric or magnetic fields in order to control and explore the interactions which create these states. Now, the same is true. It's no less different for what I'll be talking about today, which is our work on nickel disulfide. You can see the structure here with sulfur atoms in yellow and nickel in gray. Now, this is the phase diagram here. It's a function of temperature and pressure, and there's quite a few lines of magnetic order we see, but if we ignore those for the moment, just focus on the metal to insulator transition. At zero pressure and at low pressure, this material is an insulator. And as we apply a fairly large pressure, about 30 kilobar, we enter a metal. We turn the system from an insulator to a metal. It's not interesting, however, that the system, or rather it's less interesting that it becomes a metal under applied pressure, but rather that the system starts off as an insulator in the first place. In fact, a rather special type of insulator known as a Mott insulator. Now, if we think of an atom as just simply a lattice of sites in which electrons can live, there we go, okay. So in this situation, we could think of a very simple model where electrons prefer to hop. They don't like to be confined, and so we have a kinetic energy saving term of T. On the other hand, electrons, although you can fit 2 per site with opposite spin, there's a large Coulomb interaction, a Coulomb energy cost associated with that of U. And it's the balance between these 2 terms which dictate all the physics. Now, this simple model, known as the Hubbard model, is really the fruit fly of condensed matter physics theories, in that just with these 2 interaction, or these 2 considerations of hopping and repulsion, we can derive a whole bunch of emergent condensed matter phenomena from this. In fact, this model has never been fully solved. It cannot be fully solved, even numerically, at least to date. Now, if you start off with the system at half filling, 1 electron per site, this is the case in our nickel disulfide system, you ask, well, what might happen? Now, if this, here we go, if the U term is smaller than the hopping term T, then electrons can happily move through the lattice, and we have a metal. Now, as you crank up U to be much larger than T, then we ask what happens. The electrons can no longer tunnel, hop to neighboring sites, and we get a sort of gridlock, an electronic traffic jam known as a Mott insulator. Now, these sort of states are very important in condensed matter physics because many sorts of systems, such as the high TC cuprate superconductors, are either Mott insulators themselves or very closely related. The cuprates are just doped forms of Mott insulators. So Mott physics plays a large role in many other systems, and understanding this is what we aim. Now, a simple analogy of this is that if a metal is a flowing river of charge, and conventional insulator is a dried up riverbed, no more charge to flow, Mott insulator would have free charge, but by strong interactions, the charge carriers have frozen. So going back to our original picture of nickel disulfide, by applying pressure, we're changing the lattice constant, and we're changing the parameters U and T effectively in tuning between a metal and a Mott insulator. We might ask what happens right around the point where U and T are just about matched. What happens as we tune from the metal into the Mott insulator? Well, that's what our work seeks to answer. So what we want to measure is the Fermi surface of material, which is the distribution in momentum space of the electrons at the Fermi level that can participate in conduction. But we can really just think of it as a sort of a map of the velocity of the charge carriers in a metal. And so pictures of the Fermi surface, you can get something simple like for potassium, moving on to more complicated up to something like platinum, where you can have many sheets, many orbits. These things can be quite complicated. But the take-home message is that every metal has a Fermi surface, and its Fermi surface typically determines most of the properties that we would be interested in about the conduction electrons in that metal. And that's why we would wish to measure it. So how do we measure it? We use something called quantum oscillations, where if one places a metal in a large magnetic field, as a result of sort of reconciling the fact that electrons want to undergo cyclotron motion of quantized magnetic flux with the fact that there's an underlying Fermi surface, as you apply a large magnetic field, you get oscillations in the density of states, which shows up in all sorts of properties, such as resistance or the magnetization of the sample, or both, as we will measure in skin depth. And these oscillations are periodic in 1 over the magnetic field and are proportional. This frequency is proportional to the area of the cross-sections of extremal area. For this donut here, this inner orbit, the outer. And by adjusting the direction of the magnetic field, we can map out the shape and size of the Fermi surface. And this would be a typical signal, like I'll show later, for nickel disulfide for resistivity. Now, a simple way to think of this is that just as for an X-ray spectrum, an X-ray diffraction pattern, the lines can allow us to reconstruct the structure of the crystal. Here we go from quantum oscillation lines to the electronic structure of the Fermi surface. Well, we require quite large magnetic fields to do this, and so we mostly work in our quantum matter group's dilution refrigerator magnet system here in the Cavendish, where we can get up to 20.4 Tesla, about 500,000 times Earth's field, which is, of course, quite large, and yet sometimes, because these can be very small signals, this is still not large enough for us, for which we need to go to national lab facilities in Tallahassee, Florida, where they get up to 35 Tesla, or at Nijmegen in the Netherlands, up to 32 Tesla. We've worked in both facilities. Now, we would think that this isn't a large increase from the 20 Tesla that we get here at the Cavendish, but because in the regime, when our signal is suppressed, in that regime, the signal grows exponentially with magnetic field. So this can provide a huge boost, the difference between seeing nothing at all and a very good signal. And what we actually do in order to create the pressure and measure the sample is we work with the diamond amble cell technique, where we either use diamond or for lower pressures, moissanite ambles. We place a hard metal gasket on top with a hole into which we insert our coil and our sample. This is the setup. We'll hook this up to an oscillator in order to measure the skin depth of the sample. We fill the hole with pressure medium, and we squeeze together with another gem. And so by changing the force that we apply on our cell, we can tune the pressure inside up to 300 kilobar, roughly 10% of the field at the center of the Earth. So with just a simple technique, we can get great results. We see here a picture of such a cell. This is the cell body with a gem sitting on, or the amble sitting on the piston and the gasket. A close-up of the gasket and the hole here, we see the sample inside such a coil. Now, these are only 200 microns in diameter, so this is very fiddly work. It takes months of practice to get right. But, of course, with these high pressures, the reward can be great. And what do we get in the end? Well, we get a quantum oscillation signal like this at every pressure we take and every temperature. But what we want to do is, of course, extract the frequencies and the amplitudes at each frequency. So before we transform this, and that, of course, the frequencies are going to be proportional to these areas of these orbits. We see some down here at low frequency. Most prominently, we see this peak around 6 kilotesla, which density functional theory suggests would come from a cube-shaped Fermi surface pocket, a hole-like pocket, or a sheet, rather. And we're going to focus on this for the rest of the talk. So if we look at the quantum oscillation frequency as a function of pressure, as we're sitting in the metallic state and turning down in pressure, moving towards the metal-to-insulator transition, we see that really it's varying dramatically. So this orbit, the area of the area of the Fermi surface or volume is not dropping drastically as we approach. In fact, most of this change is just due to simple change of the lattice constants as we squeeze the sample. And so we see that the Fermi surface remains intact. This means the carriers remain there. They're not disappearing as we approach the metal-to-insulator transition. On the other hand, we can measure the effective mass by measuring the amplitude of this oscillation as a function of temperature. We can infer an effective mass of the carriers, which we see here appears to diverge as we approach the metal-to-insulator transition. So it seems that these carriers are getting heavier and heavier and thus effectively slower and slower until they finally stop, which is what drives the metal-to-insulator transition. And this is basically the main result of the work, that the Fermi surface remains intact. We still have carriers, but they're frozen in place. They become heavier and heavier until they stop. And so this, of course, is, well, many models have predicted no one has ever done quantum oscillation measurements up to these pressures before in order to measure in such a clean way such a transition. And so we'd like to, now that we have this technique working well, we of course want to extend this to all sorts of new materials, and that's where we're hoping to go in the future. And of course, this work was done with the help of many people. I don't have time to thank them all, but I'd particularly like to thank Hui Chang and Konstantin Semeniuk, who as graduate students really drove this project forward, and Malta Grosha, who really guided the project, as well as the people that provide the money, EPSRC. Thank you very much.
Thanks, Jordan. Okay, we have time for one question. Can't delay beer and pizza too long.
Can I ask whether close to the boundary of the metal insulator transition, The application of a voltage to
Yes.
this metal
Yes.
produces avalanche flow, or is the current always steady? Is there high frequency avalanching as part of the metal conduction?
Well, we don't know. So what we measure is the skin depth. So what we're, which in fact, we actually think most of the quantum oscillation signal in this case is coming from the magnetization, which will give the larger signal. So we have measured the resistance, but not quite with enough granularity, I would imagine, right near the transition in order to see this. In particular, it's hard to get extremely homogeneous pressure yeah, you're going to have a spread of pressure inside any given cell. So as we go right up to the transition, it's going to be very difficult to determine such a thing, even if we were actually measuring wires right on the sample. Also, it's difficult to attach wires on the sample to the sample in the first place because these start off as insulators, and those aren't fun to contact. But yeah.
Okay, let's thank Jordan again. So we're sticking to a strict schedule here. Sorry, Henning.